Hello everyone. Here is the start of exam 5, or call it the final exam, but your last exam is just going to be on the material from this point on. We start with Laplace transforms and the formal definition, and it basically takes a function f of t with an argument of t and transforms it into a function we call uppercase f of s. And the argument there is the complex argument s, as opposed to the real argument t. So it's analogous to like taking a derivative of a function. So you take a derivative of a function, you get a function. So we take the Laplace of a function and we get a function. And we use a L in front of the braces to denote the Laplace. And typically the L's fancy. I couldn't really find a fancy L on the computer. So, or it didn't really look that good. So this is how my Laplace transform L is going to look. So that's kind of a nice looking L. In any event, the idea is to take a differential equation that's in terms of this unknown function and transform it into an algebraic equation in terms of its Laplace transform. So here's the formal definition. Just given any function that's defined for t is greater than 0, the Laplace transform is this integral from 0 to infinity, e to the negative st times the function with respect to t. And that's good for all values of s for which the improper integral converges, because this is an improper integral because the upper limit of integration is infinite. So if we want to use the formal definition, which there will be one question on the exam with this, we got about 4 examples to go through here, but this would be a simple one. But to take the Laplace of this function 1, it would be the integral from 0 to infinity of e to the negative st. And I'm going to make my s's like that, because if I make them like this, they look like 5s, so my s's are going to be made, I'll use cursive, and then times the function 1 with respect to t. And so that just gives us the integral from 0 to infinity of e to the negative st. Now, formally back in Calculus 2, we used to introduce a limit to account for the infinite limit of integration. But here what we're going to do is use a what's referred to as a common abbreviation for that limit, and we're going to integrate as normal, and integrating e to the negative st, that's our formula for the integral of e to the kt with respect to t, which is 1 over k e to the kt plus a constant, of course. But so we get 1 over negative s, or negative 1 over s. But what we do is we use these square brackets right away, and we say negative 1 over s, so we integrate as normal, e to the negative st. And then we carry along the limits of integration 0 to infinity with those brackets. So that's what's referred to as a common abbreviation for, and then we introduce the limit. And we say the limit as b goes to infinity of the negative 1 over s e to the negative st from now 0 to b. And so that would be upper limit goes in, so the limit is b goes to infinity negative 1 over s e to the negative sb, or bs if you like, and then minus lower limit goes in, so minus 1 over s e to the negative s times 0, because t is the independent variable that we're integrating with respect to. So here, when we make a substitution, we get e to the negative infinity. And I'm going to show this aside. basically, when we have the situation where we have minus, let's say, we have e to the negative infinity. E to the negative infinity we can think of as the graph of e to the x. And as x approaches negative infinity, e to the negative infinity, I'm sorry, you can't see what I'm writing. As x approaches negative infinity, here's the graph of e to the negative x. E to the negative infinity we could see approaches 0 because it's the x-axis. Or you could think of e to the negative infinity as 1 over e to the infinity. And then 1 over e to the infinity is essentially infinity. And division by infinity in a limiting sense gives us 0. So therefore, you could either say by inspection that this goes to 0, or you could say negative 1 over s e to the negative infinity. And at that point, we're assuming that s is a number greater than 0. And this gives us plus 1 over s e to the 0. And we're assuming that s is greater than 0 to cause this negative exponent to always be negative. So that then we could say that this e to the negative infinity, this is in fact e to the negative infinity if s is greater than 0. And that's going to tend towards 0. And then we just get 1 over s times 1. Or 1 over s. And that would be provided that s is greater than 0. So you do need that statement saying, indicating the value of s. Okay, that is going to satisfy that equation. Okay, so that's one example. We'll kind of separate that here. And so now for this one, so Laplace of e to the 3t. First step, just substitute into the definition. So integral from 0 to infinity e to the negative st times e to the negative 3t with respect to t. Okay, and that gives us the integral from 0 to infinity of, okay, here what we're going to do is we're going to multiply these common bases, so we're going to add the exponents, and at the same time we're going to factor out a t and a negative. But I'm going to factor out the negative on the left hand side and the t on the right hand side, so that if I factor out a negative and a t from each of these, I'm left with s plus 3. Okay? And then that's with respect to t. So that's a common move that we make. Okay, so then we can integrate, and we'll use this notation here. And, the abbreviation. So we'll integrate, and we get 1 over the negative s plus 3. So let me write negative 1 over s plus 3 times e to the negative, and then s plus 3 times t, and that from 0 to infinity. Now we'll introduce the limit. So the limit as b goes to infinity of, you could actually skip a step here, but I'm gonna show this. But if you wanted to, I'm just introducing the limit at this point. If you wanted to, you could skip it that step, and you could jump right to, at the same time, using the fundamental theorem of calculus. Writing this as negative 1 over s plus 3 e to the negative s plus 3 times b, and then minus a minus 1 over s plus 3 e to the negative s plus 3 times 0. Okay, let's close my brackets here. Okay, so then that gives us, if we let b tend toward infinity, we get the limit, or we get negative 1 over s plus 3 e to the, okay, I'm going to say negative infinity, and right away I think underneath I'm going to make the statement that this is provided that s plus 3 is greater than 0. Because in order for this to be truly be a negative infinity, s plus 3 has to be a positive number. And that has to be included just like the statement here. So I guess at this point, that would have been a good notation to use. Get a slide in right there. That this must be the point where s, if that's true, that s has to be a number that's greater than 0 in order for that to be a negative infinity. So we'll make that statement there, and then minus this term, well, it becomes a plus because the double negative, and then plus 1 over s plus 3 times e to the 0. And now we could state that this tends towards 0, but again with this provision that s plus 3 is greater than 0, and then we just get the 1 over s plus 3 times e to the 0, which is 1, so 1 over s plus 3, and if s plus 3 is greater than 0, let's do the algebra over here, just s must be greater than a negative 3. Okay, and that has to be included in your final answer. Okay, so a couple more with the definition. And here we have f of t is t squared. So Laplace of t squared, by definition, definite integral 0 to infinity, e to the negative st times the function t squared with respect to t. And so that gives us integral 0 to infinity of, I'm just going to write it t squared e to the negative st with respect to t. Okay, now to integrate this one's a little tricky. You actually have to use integration by parts, and the tabular method would be the method of choice. So I'm going to set up u and dv. According to Lie 8, so we have an algebraic and an exponential. According to Lie 8, algebraic would be our u, and dv would be e to the negative st. S is the constant, t is the variable. So differentiating our u to get 0, 2t, 2, 0, differentiating e to the negative st. Every time we do, we get 1 over negative s, or negative 1 over s. So negative 1 over s, e to the negative st, another negative 1 over s, positive 1 over s squared, e to the negative st, another negative 1 over s, negative 1 over s cubed, e to the negative st. Okay, and then our diagonal products, product of the horizontal, alternate signs, plus, minus, but that final entry, since this is a 0, and we can only do that if this entry is a 0 in the u column, we can call this plus our constant of integration, because the idea is that it should be the integral of, but the integral of 0 is just some constant. Okay, so now this gives us, we'll use that abbreviation with the big brackets, so t squared, negative 1 over s, e to the negative st, I'll write as negative 1 over s, t squared, e to the negative st. Okay, next diagonal, negative 2t times 1 over s squared, e to the negative st, I'll write as 2 over s squared, t, e to the negative st, and then we have plus 2 times this negative 1 over s cubed, so that'll be negative, and I'll write 2 over s cubed, e to the negative st. And this is all from 0 to infinity. Okay, so then we can introduce that limit. So this is the limit as b tends toward infinity of this quantity, negative, just recopy. Okay, and at that point we can put in our b. Now b is tending toward infinity, but before we do substitute in the b, consider the following. And I'm going to go off to the side, I think, to show this. Okay, off to the side, I want to consider, hopefully we'll have enough room here to show this as well as the rest of the solution. I want to consider the limit as b goes to infinity of, I'll just do the t squared, e to the negative, I'm just going to do e to the negative t, so I'm assuming s is greater than 0. This limit, you actually have to use the calculus 1 rules, or 2 rules. Make it a fraction by running it as t squared over e to the t. And from there, you could use L'Hopital's rule, because now you have direct substitution would give you infinity over infinity. And so by L'Hopital's rule, you get the limit as b goes to infinity of 2t over e to the t. But that's still infinity over infinity. So you'd use L'Hopital's rule again, and you'd have the limit as b goes to infinity, t goes to infinity. Okay, I'm changing this to a t. Sorry. Just for the sake of the argument. Doesn't matter if it's t or b, because we're going to replace the t's by the b's. So, but for the sake of what I'm showing here, off to the side. Now you'd get 2 over e to the t, and that would be 2 over infinity, which is 0. Okay, now this can be shown for any power of n other than 2, any power t to the nth times e to the negative t is going to tend towards 0. And that's basically because e just gets to infinity a lot faster than t to a power does. So what I'm saying is that when we make this substitution, okay, I have to use my notation here, b and 0 is my limits now, right? When I make this substitution and I get the limit as b goes to infinity, and we plug in the upper limit, well, actually, let's not even do that. Let's just use that rule right away by inspection, because this just makes it look much more cumbersome than it needs to be. Let's just simply use that rule right away off to the side to realize that this is going to go to, this term's going to go to 0, and this term's going to go to 0, and that would be for s being greater than 0. And then we'll have that this term gives us upper limit, negative 2 over s squared, e to the negative infinity, and then minus lower limit, a minus 2 over s squared e to the 0. And so this term as well is going to tend towards 0, and that would be provided that s is greater than 0. And then it just gives us 2 over s squared times 1, or 2 over s squared. And again, this is provided that s is greater than 0. Okay, so that one's, I'm going to give you one more like number 2 on the exam, but this is just to help you with the homework, so let's just finish up this final example to kind of help you with the homework. It's a hyperbolic cosine, and with the hyperbolic cosine, what we need to do is we need to use the definition that hyperbolic cosine of t is equal to e to the t plus e to the negative t over 2. And I think in the homework you have an example for the hyperbolic sine of t, which is e to the t minus e to the negative t over 2. So the hyperbolic functions are defined in terms of the exponentials, and so therefore the Laplace of the hyperbolic cosine of t is going to be the same as the Laplace of e to the t plus e to the negative t over 2. And so we'd have the definite integral from 0 to infinity of e to the negative st times e to the t plus e to the negative t over 2 with respect to t. Okay, so now we're going to do something similar to what we did in example 2. And I'll bring out this 2 as 1/2 out in front. And then I'm going to multiply these common bases separately. So we're going to add the exponents, but at the same time we're going to factor out a t and we're going to factor out a negative. So we'll have e to the, if I factor out a t and a negative, I'm going to factor out the negative on the left. So factoring a negative from negative st, and I'm going to factor out a negative as well, so that'll leave me just with s. And then factoring out a negative and a t from e to the t, it would be s minus 1, and then times t. And you can verify that by just distributing the negative and the t. You get negative st plus 1t. And then similarly here, we'll factor out a negative on the left and a t on the right. And if I take a negative t from negative st, we're left with s. And if I take a negative t from negative t, we're left with plus 1. And that's all with respect to t. And so at this point, it gives us 1/2, and now we can integrate. We get 1 over this coefficient, so I'm going to write negative 1 over s minus 1 times e to the negative s minus 1 times t. And then similarly here, 1 over this coefficient, so I'm going to write a negative 1 over s plus 1 times e to the negative s plus 1 times t. And that's all evaluated from 0 to infinity. So then we can introduce the limit. So we have the limit as b goes to infinity. Actually, let's put the 1/2 even out in front of that limit. Okay, and then we'll have the upper limit goes in of b or no, we're not doing fundamental theorem yet, sorry. So then just recopy. Minus 1 over s minus 1 e to the negative s minus 1 times the quantity t, and then minus 1 over s plus 1 e to the negative s plus 1 times t. Okay, and then that's from 0 to b. Okay, now the fundamental theorem. So now 1/2 limit b tends toward infinity. Okay, upper limit goes in, so we get negative 1 over s minus 1 e to the negative s minus 1 times b minus this term 1 over s plus 1 times e to the negative s plus 1 times b. Okay, all minus the lower limit goes in. So minus 1 over s minus 1 e to the, I'm just going to say e to the 0, and then minus 1 over s plus 1 e to the 0, because the 0 is going in for t, so that wipes these out. Okay, and then here, these are going to go to 0 again when b tends toward infinity. But we have to claim the restrictions. And now we've got two restrictions. This is for s minus 1 being greater than 0, and this one's for s plus 1 being greater than 0. So s is greater than 1, and s is greater than negative 1. So the one that dictates to satisfy both would be the intersection, or would be this term here. Actually, I'm sorry, not that one. It would be the intersection of the two. Because if you just said greater than negative 1, like a 0 wouldn't satisfy this condition. So you have to have that. And so then finally we get 1/2 times, okay, what's here, distributing the negative and e to the 0 is 1. Just get 1 over s minus 1 plus 1 over s plus 1. And then we could do some basic algebra. Common denominator, s minus 1, s plus 1, and 1 times s minus 1 minus 1 times s plus 1 gives us 1/2 times s minus 1, s plus 1 in the denominator. And what do we get here? S minus 1 minus s minus 1. Hold on a second. Yeah, I'm sorry, I made a mistake here. This should have been a plus 1 times s plus 1, so plus s plus 1. Okay, and then we get 1/2 times, finally, 2s over, and then you could multiply this out, you get s squared minus 1, and the 2's cancel, and finally we get s over s squared minus 1. And the provision would be the one that is the intersection is s is greater than 1. Okay, so that's the definition, and we'll come back next time and we'll see how to use a table rather than having to go through all this formality.